Tonight, we're going to travel to the edge of everything that exists. Not the edge of our solar system, not the edge of our galaxy, the edge of the universe itself. The place where space, as we understand it, simply stops. And what lies beyond that boundary is something science can barely describe. Something the human mind was never built to fully grasp. Something that, when you sit with it long enough in the quiet of the night, feels less like a fact and more like a dream you cannot wake up from. Here is the thing most people don't realize. When you look up at the night sky and see those distant points of light, you are not seeing the universe. You are seeing a bubble. A sphere of reality roughly 93 billion light-years across, lit from within by 2 trillion galaxies, each one containing hundreds of billions of stars. That bubble is everything science has ever observed, everything telescopes have ever reached, everything the light of creation has had time to deliver to your eyes. And it has an edge, a hard, absolute, terrifying edge. Beyond it, the laws of what we can know collapse entirely. Beyond it, there may be more universe stretching on for trillions of times the distance we can see. Or there may be something so alien to our understanding that the word universe no longer applies. And here is what makes that edge truly haunting. It is moving away from us right now faster than light itself. Every second you breathe, more of reality slips permanently beyond our reach. By the end of tonight, you are going to understand exactly why that boundary exists, what cosmologists believe hides behind it, and why staring toward the edge of the universe is, in the most profound sense, the most terrifying and beautiful thing a human mind can do. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. There is a place at the end of everything, not a metaphor, not a poetic idea invented to make the universe feel more dramatic, an actual boundary, a real and measurable limit where the observable cosmos simply stops. Where the last light we will ever detect fades into a wall of ancient radiation, and beyond that wall the universe continues in ways we cannot see, cannot reach, and may never fully understand. Tonight, you and I are going to travel there together, slowly, quietly, one step at a time, the way you walk toward the edge of a cliff in the dark, not rushing, because rushing would mean missing the immensity of what surrounds you on the way. I want you to take a breath before we begin. Just one slow breath in and let it out. Because what we are about to explore is not something you absorb with urgency. It is something you absorb the way the night absorbs sound, gradually, completely, until the silence becomes part of you, and the scale of what we are discussing settles into your body like the weight of a heavy blanket, warm and vast and still. This is a long journey. There is no need to hurry. The edge of the universe has been there for 13.8 billion years. It will still be there when we arrive. Let me start with something familiar. Something you have seen 100 times without ever quite thinking about what it means. On a clear night, away from city lights, you can look up and see roughly 5,000 stars with your naked eye. 5,000 points of light scattered across the dome of the sky like scattered grains of salt on black velvet. That number already feels large. It already feels like more than you could count in a single sitting. But here is the thing most people do not realize. Those 5,000 stars are all within a few thousand light-years of Earth. They are, in cosmic terms, your immediate neighborhood, your front yard, the patch of grass right outside your door, and the universe extends beyond that neighborhood for distances so extreme, so completely outside normal human experience, that every analogy eventually breaks down. Our galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. That number is almost impossible to hold in the mind. If you counted one star per second, it would take you more than 3,000 years just to count to 100 billion. And the Milky Way is just one galaxy. Just one island of light in a cosmos that contains an estimated 2 trillion galaxies. 2 trillion, each one a collection of hundreds of billions of stars, many of them with their own planets, their own systems, their own vast and silent histories. The scale compounds on itself until your mind simply releases its grip and floats free, unable to anchor to anything recognizable. And yet, all of that, every single one of those 2 trillion galaxies, everything every telescope ever built has ever recorded, every photon of light that has ever travelled across space and arrived at a human eye or a camera lens, all of it fits inside a sphere we call the observable universe. 93 billion light-years across. That is the bubble we live inside. That is the totality of what we can detect, what we can measure, what we can know through the tools of science. It is unimaginably large. It is also, in the most literal sense possible, a cage. A beautiful, luminous, terrifying cage defined not by walls but by time. By the simple fact that light travels at a finite speed and the universe has only existed for a finite duration. We can only see as far as light has had time to reach us. Beyond that distance, the information simply does not exist yet. It has not arrived. It may never arrive. Because here is where the story deepens. Here is where the quiet strangeness of the universe begins to reveal itself. The edge of our observable bubble is not a static thing. It is not a fixed fence sitting patiently in space, waiting to be crossed. The universe is expanding. Space itself is stretching in every direction, carrying galaxies away from each other like dots on the surface of an inflating balloon. And that expansion is accelerating. The galaxies at the far reaches of our observable universe are already moving away from us faster than light can travel. Not because they are breaking the cosmic speed limit, but because the space between us and them is growing faster than light can cross it. Which means there are galaxies we can see right now, tonight, visible in our telescopes at this very moment, that we can never reach. Not ever. No matter how fast a spacecraft we built, no matter how many generations made the journey, those galaxies would always be receding faster than we could approach. We can see them. We are forever separated from them. That idea, that vision without possibility of contact, is one of the most quietly devastating things in all of cosmology. It means that what we call the universe is really just a pocket of knowability inside something far larger and far stranger. A lit room inside a structure whose outer walls we cannot find, whose total size we do not know, and whose contents beyond our walls may be so alien to our understanding that our current vocabulary has no words for them. Some cosmologists believe the universe beyond our horizon extends trillions of times farther than what we can observe. Others believe it may be literally infinite, going on forever in every direction without boundary or center or edge. And a smaller but serious group believes our universe is just one of countless others, a single bubble in an eternal foam of realities, each one born from a different quantum fluctuation, each one governed by potentially different laws of physics. Tonight, we're going to explore all of it. We're going to start here, in this familiar pocket of light and matter, and walk outward, step by step, until we reach the edge of what we can know, and then we're going to stand at that edge and look outward into what lies beyond. We will look at what the cosmic microwave background tells us about the boundary of perception. We will examine what dark energy is doing to the size of the observable universe, and why the edge is moving away from us faster every year. We will explore the mathematics of a universe that might be flat and infinite, or curved and finite, or shaped like something with no name in human geometry. And we'll sit for a while in the most uncomfortable question of all. If the universe has an edge and something lies beyond it, what is that something? What word do you use for the space outside of space? What concept holds the container of all existence? These are not easy questions. They are not questions with clean answers you can write on a whiteboard and walk away from. They are the kind of questions that expand the longer you hold them, the way your eyes adjust to darkness and slowly reveal shapes you could not see at first. They are questions worth sitting with tonight, in the dark, as you drift between wakefulness and sleep. Because somewhere in that threshold state, the mind loosens its need for certainty and becomes capable of something more useful: wonder. Pure, unhurried, oceanic wonder at the fact that we exist at all, that we are aware, that we have developed instruments sensitive enough to detect light from 13 billion years ago, and that we have the audacity to ask what lies beyond the last thing we can see. So settle in. Let your body soften into wherever you are resting. Let the weight of the day release. Because tonight, we're going somewhere very few people allow themselves to truly go. We're going all the way to the edge of the universe. And what waits for us there is stranger, larger, and more beautiful than anything you have ever been told. Let me paint a picture for you. Imagine you are standing in the middle of a vast, dark ocean. In every direction, as far as your eyes can reach, you see water, waves moving slowly, starlight reflected on the surface. the horizon curving away from you in a perfect circle, equidistant in every direction, because that is simply how far your eyes can see from where you stand. Beyond that horizon there is more ocean. You know it is there. Ships have gone that way and returned. The mathematics confirms it. But from where you stand in this moment, that horizon is your limit. Everything beyond it is hidden, not because it does not exist, but because the curve of the Earth carries it below your line of sight. Now take that image, stretch it into 3 dimensions, multiply the distance by a factor so large it has no comfortable name, and replace the ocean with space, the horizon with the edge of the observable universe, and the curvature of the Earth with the finite speed of light travelling across 13.8 billion years of cosmic history. That is roughly where we are tonight. The observable universe is the sphere of space from which light has had enough time to reach us since the Big Bang. It is not the whole universe. It is the portion of the universe we can currently detect. The distinction matters enormously, and it is one of those things that sounds simple the first time you hear it, but becomes progressively more staggering the longer you think about it. Light travels at approximately 186,000 miles per second. That is fast enough to circle the Earth 7.5 times in a single second, and yet across the distances of deep space, even that extraordinary speed becomes almost unbearably slow. Light from our moon takes just over 1 second to reach us. Light from the Sun takes about 8 minutes. Light from the nearest star beyond our Sun, Proxima Centauri, takes 4.2 years. Light from the centre of our own Milky Way galaxy takes 26,000 years. And light from the most distant galaxies we have ever observed takes over 13 billion years to arrive. When you look at a galaxy that far away, you are not seeing it as it is. You are seeing it as it was more than 13 billion years ago, when the universe was less than 1 billion years old. This is one of the most beautiful and quietly unsettling properties of the universe. Every observation we make is an observation into the past. Your eyes are time machines. The further you look, the further back in time you see. When you look at the Andromeda Galaxy on a clear night, that smudge of light left its source 2.5 million years ago, when our ancestors were small-brained hominids walking the African savanna. The photons entering your eye tonight began their journey before Homo sapiens existed. They have been travelling through empty space for 2.5 million years, and they end their journey inside your eye in this moment as you lie here in the dark. That is not a metaphor, that is physics, and it applies to everything in the sky, at every distance, all the way out to the farthest detectable edge of the cosmos. So what exactly is out there, between here and that edge? The structure of the observable universe is something astronomers have spent decades mapping, and what they have found is both magnificent and deeply strange. Matter is not spread evenly through space, it is clustered. Galaxies gather together into groups, groups gather into clusters, clusters gather into superclusters, and superclusters form enormous filaments and sheets of matter that stretch across hundreds of millions of light years, separated by vast voids of almost complete emptiness. Scientists call this the cosmic web. If you could shrink the observable universe down to the size of a human brain, the cosmic web would look remarkably similar to neural tissue. Dense knots of matter connected by long filaments surrounding hollow cavities where almost nothing exists. The universe, at the larger scales, looks like a thinking organ. Whether that resemblance means anything at all is a question best saved for the edge of sleep. Within this cosmic web sit an estimated 2 trillion galaxies, though that number has been revised upward several times as our telescopes improve. 2 trillion is a number that genuinely resists comprehension. If every person alive on Earth today were to count galaxies, 1 per second, without stopping, without sleeping, it would take the entire human population working simultaneously more than 8,000 years to count them all. Each of those galaxies contains between 10 billion and 1 trillion stars. Some galaxies are elliptical and ancient, slowly fading like embers. Some are spiral, like our own Milky Way, with arms of young blue stars sweeping through a disk of gas and dust. Some are irregular, torn apart by collisions or gravitational interactions with neighbours. And every single one of them, in every shape and size and age, is moving away from every other one as the universe expands, carried outward on the stretching fabric of space itself. Now, here is something that most people gloss over when they first learn about the observable universe, but which I think deserves a moment of genuine stillness. The edge of the observable universe is not a fixed distance of 13.8 billion light-years, even though the universe is 13.8 billion years old. You might expect those numbers to match. Light that left the edge of the universe at the moment of the Big Bang and has been travelling toward us for 13.8 billion years should be 13.8 billion light-years away, right? But the actual radius of the observable universe is approximately 46.5 billion light-years. The reason is expansion. The regions of space that emitted the light we are only now receiving have been moving away from us the entire time that light was in transit. By the time the light arrives, the source is far further away than it was when the journey began. The universe has been stretching and growing the whole time, carrying those distant regions ever further from us even as their ancient light completes its crossing. The observable universe is therefore bigger than you would expect from the age of the universe alone, precisely because space itself has been expanding beneath the light as it travelled. And here is where the first layer of true mystery opens. Beyond that 46.5 billion light-year radius, the universe does not stop. There is no wall, no membrane, no door marked with a sign indicating the end of everything. The cosmos simply continues, in all directions, beyond our ability to detect it. How much further it goes, nobody knows. Current measurements suggest that the universe is geometrically flat, which in cosmological terms implies it may be infinite in extent. But even if it is finite, even if it has some enormous but bounded size, that total size could dwarf our observable bubble by a factor that makes the 2 trillion galaxies we know about feel like a single grain of sand on an infinite beach. We are not at the centre of the universe. There is no centre. Every observer in every galaxy, no matter where they are, sees an observable universe centred on themselves, with the same 46.5 billion light-year radius, bounded by the same horizon of ancient light. We each live inside our own bubble of knowability, and those bubbles may overlap or they may not, depending on where those other observers are located in the vast uncharted territory beyond our own horizon. Take a moment with that. Let it settle. You are lying here tonight inside a bubble of light and information, surrounded by 2 trillion galaxies visible to science, embedded in a cosmic web of matter that stretches in every direction, orbiting a star in one spiral arm of one of those galaxies on a small rocky world that has existed for 4.5 billion years. And all of that, the entire luminous contents of your observable universe, is just the lit room, just the small circle of firelight you happen to be sitting inside. The rest of the universe, the part you cannot see, the part no human instrument has ever detected or will ever detect, stretches away into a darkness so complete and so vast that even the word infinite feels too small to contain it. Tonight, we're going to keep walking toward that darkness, step by step, and I promise you, the further we go, the more beautiful and terrifying it becomes. There is a wall at the edge of everything we can see, not a wall made of matter, not a wall made of energy in any conventional sense, a wall made of light, ancient light. Light so old it was born before any star existed, before any galaxy had formed, before the universe had cooled enough to allow a single atom to hold itself together. It is the oldest thing we have ever detected. It is the farthest signal that has ever reached us, and it sits at the very boundary of our observable universe like a curtain drawn across the cosmos, hiding everything that came before it and everything that lies beyond it, from our instruments, our telescopes, and our understanding. Tonight, we are going to stand in front of that wall, we are going to look at it very carefully, and we are going to ask as quietly and as seriously as we can what might exist on the other side. To understand this wall of light, you need to travel back in time, not just a few thousand years, not even a few million. You need to go back 13.8 billion years to a moment so early in the history of the universe that the concepts we use to describe ordinary reality barely apply. In the first fraction of a second after the Big Bang, the universe was a place of almost unimaginable density and heat. Everything that exists, all the matter and energy that would eventually become 2 trillion galaxies, stars, planets, oceans, and the atoms inside your body right now, was compressed into a space smaller than a single proton. The temperature was not millions of degrees, not billions, not even trillions. In those first instants, the temperature of the universe was so extreme that physicists describe it with numbers that have more zeros than most people encounter in a lifetime of mathematics. It was a place where the laws of physics as we know them may not have yet solidified, where reality itself was still deciding what it wanted to be. As the universe expanded and cooled, something began to happen. Matter started to organize. The simplest particles, quarks and electrons and photons began to interact in structured ways. For the first roughly 380,000 years of the universe's existence, the cosmos was filled with a dense, opaque plasma. Think of it like the interior of a star, but everywhere, in all directions, with no outside, no boundary, just a hot, luminous fog extending across all of space simultaneously. In this plasma, photons of light could not travel freely. They were constantly colliding with charged particles, scattering in all directions, unable to move more than a tiny distance before being absorbed or deflected. The universe was not transparent. It was a brilliant, glowing fog, and nothing, not even light, could see through it. Then, approximately 380,000 years after the Big Bang, something changed. The universe had cooled enough to a temperature of roughly 3,000 degrees for electrons to combine with protons and form the first neutral hydrogen atoms. This moment has a name in cosmology. It is called recombination, though it is somewhat misleadingly named since the electrons and protons had never actually been combined before. The critical thing about recombination is what it did to the fog. When neutral atoms formed, the photons that had been trapped, bouncing endlessly through the plasma, were suddenly free. There was nothing left to scatter them. The fog lifted. The universe became transparent in an instant, cosmologically speaking, and all those photons that had been imprisoned in the plasma streamed outward in every direction, carrying with them a snapshot of the universe as it existed at that precise moment. That flood of liberated light has been travelling through space ever since. It has been travelling for 13.8 billion years. And it is arriving at Earth right now from every direction simultaneously as a faint glow of microwave radiation that permeates all of space. We call it the cosmic microwave background. The cosmic microwave background, or CMB, was first detected accidentally in the year 1965 by two radio astronomers named Arno Penzias and Robert Wilson. They were working at Bell Telephone Laboratories in New Jersey, using a large horn-shaped antenna to study radio signals from space. No matter which direction they pointed their antenna, they detected a persistent uniform hiss of microwave radiation that they could not explain. They checked their equipment, they cleaned the antenna, removing what they diplomatically described as a white dielectric material, which was in fact pigeon droppings. The noise persisted. It came from everywhere equally. It was not a local signal, it was not interference. It was the afterglow of the Big Bang itself, arriving at their antenna from every corner of the universe simultaneously. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for a discovery they initially thought was a malfunction. What makes the CMB so extraordinary and so relevant to our journey tonight is what it represents as a boundary. That wall of ancient light marks the absolute limit of what any optical or radio telescope can ever see. When we look out to the edge of the observable universe, we're not looking at empty space beyond the last galaxy. We are looking at this glowing surface, this sphere of last scattering, as astronomers call it, where the fog of the early universe finally cleared. Everything we can observe, every galaxy, every quasar, every filament of the cosmic web, exists between us and that surface. The CMB is the back wall of the observable universe. It is the furthest thing our instruments can detect. And crucially, it is not a wall in space, it is a wall in time. When you look at the CMB, you are looking at the universe as it existed 380,000 years after its birth. You are looking at the last moment before the cosmos became transparent. You cannot see further back than that with any electromagnetic telescope, because before that moment, the universe was opaque. The light from those earlier times never escaped. It was absorbed into the plasma, and it is gone. And yet, the CMB is not just a boundary, it is also a map. The temperature of the CMB is not perfectly uniform. It varies by tiny fractions of a degree, patterns of slightly warmer and slightly cooler regions that were imprinted on that surface at the moment of last scattering by the distribution of matter in the early universe. These tiny fluctuations, these ripples in the ancient light, are the seeds of everything that came after. The slightly denser regions of the early universe eventually collapsed under gravity to form the first galaxies, the first stars, the cosmic web we see today. The CMB is not just the oldest light we can detect. It is the blueprint of the universe. It is the moment the cosmos showed its hand and revealed the initial conditions from which all of existence, including you and I, eventually emerged. Scientists have mapped this ancient light with extraordinary precision using satellites, and the patterns they find confirm our best models of how the universe began, and hint at physical processes that occurred in the first fraction of a second after the Big Bang, times so early that no direct observation will ever reach them. But here is what I want you to hold in your mind as you rest tonight. Beyond that wall of ancient light, beyond the surface where the fog lifted and the photons flew free, there is more universe, more space, more matter, more of whatever the cosmos is made of. The CMB is not the end of reality. It is the end of what light can show us. It is the horizon of our perception, not the boundary of existence. What lies on the other side of that glowing wall is one of the great open questions in all of science. More galaxies, almost certainly. Perhaps regions of space so distant from us that no signal from them will ever reach us, no matter how long we wait. The wall of light is humbling precisely because it is not a wall at all. It is a limit built into the nature of observation itself, a reminder that the universe does not owe us access to its full extent, that knowing has edges the same way that space does, and that some of the most important truths about the cosmos may be permanently, irrevocably out of reach. That is not a failure of science, that is a fact about reality. And tonight, rather than feeling diminished by it, I want you to feel the strange, quiet wonder of it. We found the edge of what we can see, we mapped it. We read its patterns, and we know, with certainty, that something vast and uncharted lies beyond it. When most people hear the phrase the edge of the universe, they picture something like the edge of a table, a flat surface that simply stops, a place where you could stand with your toes over the boundary and look down into whatever lies beyond. Maybe empty space, maybe darkness, maybe nothing at all. That image is intuitive, deeply human, and almost completely wrong. The edge we're talking about tonight is not a physical barrier you could approach in a spacecraft. It is not a line drawn in space that you could cross if you travelled far enough in the right direction. It is something far stranger, far more conceptually demanding, and in many ways far more terrifying than a simple boundary. It is a limit built into the nature of time and light themselves. And understanding it properly requires us to loosen our grip on the way we normally think about space and distance and reality. Let me offer you a thought experiment. Imagine you are standing in a lighthouse in the middle of an ocean at night. The beam of your lighthouse reaches outward in all directions, illuminating a circle of water around you. Beyond the edge of that circle, there is darkness. You cannot see what is out there. It is not that nothing exists beyond the reach of your light. The ocean continues. There may be islands, ships, other lighthouses, entire coastlines that your beam simply does not reach. The boundary of your illuminated circle is not a boundary of the ocean. It is a boundary of your perception, defined entirely by the power of your light source and the darkness of the night. Now imagine that the ocean is not static but expanding, and that the further away a piece of ocean is from you, the faster it is moving away. At some distance, pieces of ocean are moving away faster than your light can travel. Your beam can never catch them. They are gone, not because they cease to exist, but because the expanding ocean carries them beyond your reach faster than light itself can follow. That, in rough terms, is the edge of the observable universe. It is the edge of your lighthouse beam, not the edge of the ocean. Cosmologists are very careful about the language they use here, and for good reason. There are actually several different things that people mean when they say the universe has an edge, and conflating them leads to enormous confusion. The first meaning is the edge of the observable universe, the boundary we have been discussing, defined by how far light has had time to travel since the Big Bang. This edge is real, measurable, and sits at a radius of approximately 46.5 billion light-years in every direction from Earth. The second meaning is the edge of the universe itself, the total extent of all space, whether observable or not. This is unknown. It may be infinite. It may be finite, but vastly larger than the observable portion. The third meaning, and perhaps the most philosophically challenging, is the question of whether space itself has an end. a place where the geometry of the cosmos terminates. Each of these meanings points to a different question, a different mystery, and a different flavour of the vertigo that comes from thinking about the largest possible scales of reality. Here is the thing most people do not realise about the observable edge specifically. It is not the same for everyone. Every observer in the universe, no matter where they are located, has their own observable universe centred on themselves, with their own 46.5 billion light-year radius. An astronomer in a galaxy 10 billion light-years from Earth has an observable universe that overlaps with ours, but extends 10 billion light-years further in the direction away from us. They can see things we cannot. We can see things they cannot. There is no privileged centre to the observable universe, just as there is no privileged centre to the cosmic expansion. Every point in space is simultaneously the centre of its own observable bubble, and every one of those bubbles has its own edge, its own horizon, its own wall of ancient light. The universe does not have one edge. It has as many edges as there are observers to define them. Each awareness creates its own boundary. Each mind draws its own circle of knowability around itself, and beyond every one of those circles the cosmos continues undisturbed and unknowing. Now let me tell you the part that I find genuinely, quietly devastating. There are galaxies we can see right now, detectable with our current telescopes, that we can never reach. Not because of the distance alone, not simply because they are too far away, but because the expansion of space between us and them is already carrying them away faster than any spacecraft could travel, faster than light itself can cross the widening gulf. These galaxies are visible. Their light has already made the journey and arrived at our telescopes. But if we sent a signal toward them today, that signal would never arrive. The space between us and them is growing faster than the signal could traverse it. We can see them. We know they exist. We can study their stars and measure their motion, and we are permanently, irrevocably separated from them. They are visible but unreachable, known but inaccessible. The universe has placed them on the other side of a one-way boundary, and that boundary is not a wall in space. It is a consequence of physics, of dark energy, of the accelerating expansion of the cosmos, of time itself. This concept has a name. Cosmologists call it the cosmic event horizon, distinct from the observable universe's edge. The cosmic event horizon marks the boundary beyond which events can never affect us, ever, no matter how much time passes. It sits at a distance of approximately 16 billion light-years from Earth at this moment, closer than the edge of the observable universe because the expansion has already placed galaxies between 16 and 46 billion light-years from us, in a region where we can see their past light but can no longer influence or be influenced by their future. Inside our event horizon, signals and interactions are still theoretically possible. Outside it, connection is severed. Forever. The horizon is not just the edge of what we can see. It is the edge of what we can ever touch, affect, or be part of. It is the border of our causal universe, the domain within which our existence has any meaning for the rest of reality. And here is where the strangeness deepens one more layer. Because both of these edges, the observable horizon and the event horizon, are moving. As time passes and the universe expands, our event horizon is actually shrinking in terms of the co-moving volume it encloses. Fewer and fewer regions of space remain within reach. Galaxies that are today marginally within our ability to influence will drift beyond our horizon in the cosmic future, joining the growing territory of the permanently unreachable. The universe is not just large and old. It is actively reducing the domain of possibility available to any observer within it. The cage, if you want to use that word, is getting smaller. Not because we are moving inward, but because the walls are moving outward faster than light. The accessible universe is contracting, one galaxy at a time, into an ever smaller sphere of connection and meaning. I want you to sit with that for a moment. Not with anxiety, not with the impulse to solve it or push it away. Just sit with it, the way you would sit beside a very deep lake at night and look at the darkness of the water without needing to know how deep it goes. The universe has edges, multiple kinds of edges of perception, edges of causality, edges of time, edges of the knowable. And all of them point in the same direction, outward, into a vastness that does not require our awareness to exist, that was old before the first star was born, and that will continue long after the last light in the observable universe has faded. The edge is not the end of reality. It's the end of our portion of it, And that distinction, small as it sounds, is perhaps the most important thing you will carry with you from tonight. In the year 1929, an astronomer named Edwin Hubble made an observation that changed everything. Working at the Mount Wilson Observatory in California, using what was at the time the most powerful telescope in the world, Hubble studied the light coming from distant galaxies and noticed something that nobody had expected. The light was shifted toward the red end of the spectrum. Not just from one galaxy, not just from a few, from virtually every galaxy he could observe, in almost every direction he looked. The further away a galaxy was, the more its light was shifted toward red. Hubble understood what this meant. The galaxies were moving away from us, all of them, in every direction simultaneously. The universe was not static and eternal, as most scientists had assumed. It was expanding. Space itself was growing, carrying galaxies apart from one another the way raisins in a rising loaf of bread are carried apart, not because the raisins are moving through the bread, but because the bread itself is expanding between them. That discovery was the beginning of modern cosmology, but it was also the beginning of a question that would take another 70 years to answer, and whose answer, when it finally came, was one of the most shocking things science has ever uncovered. If the universe is expanding, what is driving that expansion? For decades after Hubble's discovery, the assumption was that the expansion must be slowing down. Gravity, after all, is attractive. All the matter in the universe pulls on all the other matter. The galaxies flying apart from each other should be gradually decelerating, like a ball thrown upward that slows as gravity pulls it back. The open question was simply whether there was enough matter in the universe to eventually halt the expansion entirely and reverse it into a contraction, a big crunch, or whether the universe would expand forever, but at an ever-decreasing rate. In the 1990s, two independent teams of astronomers set out to measure exactly how much the expansion was slowing. They used a particular type of exploding star called a Type 1a supernova as a cosmic measuring tool, because these explosions always produce roughly the same peak brightness, making them reliable distance markers across billions of light years. They measured the distances and speeds of supernovae in distant galaxies, expecting to find the deceleration they knew must be there. What they found instead was so unexpected that the team spent months checking their instruments, rechecking their data, and searching for errors before they would accept what the numbers were telling them. The expansion of the universe was not slowing down. It was speeding up. The universe is not just expanding, it is accelerating. Every second that passes, the galaxies of the cosmos are flying apart from one another faster than they were the second before. Something is pushing space to grow at an increasing rate, overcoming gravity on the larger scales, driving the universe toward a future of ever greater separation and ever deeper cold and darkness. That something has a name. We call it dark energy. And here is the terrifying part. We have almost no idea what it is. We cannot detect it directly. We cannot produce it in a laboratory. We cannot point a telescope at it. We know it exists only because of its effect, the accelerating expansion it drives, the way you might infer the existence of wind not by seeing it but by watching the trees bend. Dark energy does not interact with matter or light in any way we can measure. It simply permeates space uniformly, in every region of the universe simultaneously, and it pushes, constantly, relentlessly, with a force that grows more dominant over gravity with every passing billion years. And according to our best current measurements, dark energy makes up approximately 68% of the total energy content of the universe. The majority of everything that exists is something we cannot see, cannot touch, and do not understand. To feel the true weight of the acceleration, let me give you some numbers. Right now, galaxies at a distance of about 14 billion light-years from us are receding at approximately the speed of light. Galaxies further than that are receding faster than light, not because those galaxies are moving through space at superluminal speeds, which would violate the laws of physics, but because the space between us and them is expanding at a rate that, when you add up all the stretching across those vast distances, produces a recession velocity that exceeds the speed of light. There is no violation of relativity here. Space itself is not bound by the cosmic speed limit. Only objects moving through space are. But the practical consequence is absolute and final. Those galaxies are beyond our reach. Their light, travelling toward us at the maximum possible speed, is losing ground to the expansion of space. They are receding faster than their own light can approach us. Any signal we sent toward them today would travel forever through an expanding universe and never arrive. The distance is not just large, it is growing, it is accelerating, it is, in the most literal sense, running away. Now consider what this means for the edge of the observable universe over time. As the expansion accelerates, more and more galaxies cross our event horizon. Galaxies that are today just barely within our cosmic reach will, over the next tens of billions of years, be carried beyond the point of no return, joining the unreachable territory outside our causal horizon. In roughly 150 billion years, every galaxy currently visible except the few dozen gravitationally bound to our own local group will have receded beyond our horizon. The night sky of that era, if any civilization existed to observe it, would appear almost entirely empty. No distant galaxies, no cosmic web, no evidence whatsoever that the universe contains anything beyond a small cluster of local stars and stellar remnants. A civilization born in that future epoch, with no record of our current astronomical knowledge, would have no way of knowing that 2 trillion galaxies had once been visible. They would look out into darkness and conclude, reasonably but incorrectly, that their small cluster of matter was essentially all that existed. The accelerating expansion is not just separating us from the rest of the universe, it is erasing the evidence that the rest of the universe was ever there. Here is something I find almost unbearably poignant about this picture. We are living in what cosmologists sometimes call the golden age of observational astronomy, not because our technology is the most advanced it will ever be, but because we happen to exist at a moment in cosmic history when the universe is still young enough and the expansion still slow enough that we can see almost its entire observable extent. We are witnessing a view of the cosmos that will never be available again. Every billion years that pass, the view becomes smaller, the horizon closer, the evidence of the greater universe more thoroughly erased by the accelerating expansion. Our descendants, if they exist in the deep future, will inherit a diminished sky. They will know less about the true scale of the cosmos than we do today, not because they will be less intelligent or less technologically capable, but simply because the universe will have hidden more of itself behind the growing curtain of the expansion. We are not just lucky to exist. We are lucky to exist now, at this precise moment in cosmic history, when the sky is still full of light from 2 trillion galaxies, and the evidence of our cosmic origins is still readable in the ancient glow of the microwave background. Dark energy, then, is not just an abstract physical curiosity. It is the force that defines the ultimate fate of everything you can see tonight. It is the engine of cosmic isolation, the mechanism by which the universe gradually severs its own connections, drawing everything into smaller and smaller islands of light separated by ever vaster oceans of empty, accelerating space. It is the reason the edge of the observable universe is not a fixed address, but a moving boundary retreating from us in every direction as the expansion carries it away. And it is perhaps the single most important reminder that the universe operates on timescales and with forces entirely indifferent to human experience, human curiosity, or human longing. The universe does not expand because anything wills it to. It expands because the geometry of space and the mysterious energy woven into its fabric demand it. And tonight, as you lie here in the quiet dark, the expansion continues. Silent, constant, carrying the far galaxies a little further away with every breath you take. I want you to imagine a night sky unlike any you have ever seen. Not the sky above a city, washed out by artificial light. Not even the sky above a remote desert or a mountaintop brilliant with stars and the pale arch of the Milky Way. I want you to imagine the deepest, richest, most complete night sky that physics will ever allow. Every star your eye can resolve, every smear of distant galaxies visible as faint clouds between the constellations, the full observable universe on display above you, 2 trillion galaxies spread across the dome of the night in a tapestry of ancient light. That sky, that extraordinary vision is what exists right now, tonight. This version of the universe, with its crowded horizon and its luminous cosmic web, is what we have inherited by the accident of being born at this particular moment in cosmic history. And according to everything we understand about dark energy and the accelerating expansion, it will not last. The sky is going dark. Not tonight, not in any human lifetime. But on the timescale of the universe, the clock is already running and the lights are already beginning, one by one, to go out. To understand what is coming, you need to think about the local group. The local group is the small family of galaxies to which our Milky Way belongs. It contains roughly 80 galaxies in total, most of them small dwarf galaxies, but anchored by two large spirals, our own Milky Way and the Andromeda Galaxy, which sits approximately 2.5 million light-years away. These galaxies are gravitationally bound to one another. Gravity holds them together in a tight enough embrace that the accelerating expansion of the universe cannot pull them apart. In fact, Andromeda and the Milky Way are not moving apart at all. They are moving toward each other. In approximately 4.5 billion years, they will collide and eventually merge into a single large elliptical galaxy, a slow-motion cosmic collision that will rearrange billions of stars over hundreds of millions of years without most of those stars ever coming close to one another, simply because the distances between stars even within a galaxy are so enormous. After that merger, the resulting galaxy, sometimes called Milkomeda by astronomers with a taste for portmanteau, will be the dominant structure of our gravitationally bound local group. And that local group, that small island of matter held together by its own gravity, is essentially the entire inheritance of any civilization that exists in the far future, because everything else is leaving. All the other galaxy clusters, all the other superclusters, all the filaments of the cosmic web beyond the gravitational reach of our local group are being carried away by the accelerating expansion. And the further away they are, the faster they recede. Within roughly 100 billion years, which is roughly 7 times the current age of the universe, every galaxy outside our local group will have crossed our cosmic event horizon. Their light, already ancient by the time it reaches us, will no longer be able to make the crossing. The expanding space between us and them will grow too fast for even a photon to bridge. One by one, galaxy cluster by galaxy cluster, the lights on the horizon will simply stop arriving. Not because those galaxies will have died, many of them will still be burning with billions of stars, but because the space between us and them will have stretched beyond the point where any signal can cross. They will vanish from our sky the way a ship disappears over the horizon of the ocean, slowly, then completely, then as if they never existed at all. What remains after that great cosmic dimming is an island, a single gravitationally bound structure, the merged remnant of our local group, surrounded in every direction by absolute darkness. No galaxies on the horizon, no cosmic web, no faint smears of light from distant clusters, just the stars of our own island, burning in a void so complete and so vast that the word empty does not adequately describe it. Future astronomers, if they exist, will look outward from that island and see nothing, literally nothing. Not dark matter halos they cannot detect. Not the afterglow of the Big Bang. Nothing that any instrument they could build would register as a signal from beyond their cosmic shore. The cosmic microwave background itself, that ancient wall of light we discussed, will have redshifted to such extreme wavelengths by then that its temperature will be indistinguishable from absolute zero, undetectable against the background of space. The universe will have hidden its own history so thoroughly that its origin, its age, its true scale will all be beyond the reach of any future science built in that isolated island. Here is the thing most people do not realize about this picture. It is not a speculation about some exotic or unlikely scenario. It is the straightforward prediction of our best confirmed cosmological model using measurements of dark energy that have been verified independently by multiple methods across decades of research. Barring some fundamental revision of physics, the future universe will be an archipelago of isolated gravitational islands, each one separated from every other by distances so vast and expansion rates so extreme that no communication between them is possible. The universe is not headed toward connection and unity. It is headed toward isolation and silence. Each island of matter drifting further into its own private darkness, unable to see or signal or affect any other. The large-scale structure of the cosmos, that magnificent cosmic web of filaments and clusters that took billions of years to form, is a temporary feature of a young universe. Gravity built it in the first few billion years. Dark energy is patiently, unstoppably dismantling it over the next 100 billion. There is something deeply affecting about this trajectory when you sit with it in the quiet of the night. The universe we inhabit right now, the one with its crowded galaxies and measurable cosmic background and readable history written in the light from distant quasars, is the universe at a moment of extraordinary legibility. We can look outward and see evidence of the Big Bang. We can map the cosmic web. We can detect the afterglow of the first light. We can observe galaxies in the process of formation 13 billion years ago. All of this is available to us right now, because we exist at a cosmically early moment when the expansion has not yet erased the evidence. We are reading a book that is slowly being burned, not maliciously, not tragically in any cosmic sense, simply as a consequence of physics unfolding on timescales that dwarf human comprehension, but burned nonetheless. Future generations, billions of years from now, will inherit a universe that has forgotten its own past, a cosmos with no record of its own origin, no visible evidence of its own scale, and no way to know that it was ever anything other than a single island of aging stars in an infinite dark sea. And yet, I do not want you to hear this as a cause for despair. Consider instead what it means that we are here now, at this precise and fleeting moment in the life of the universe, when the sky is still full and the horizon is still luminous, and the history of creation is still written in the light coming through our telescopes. We are not just lucky to be alive, we are lucky to be alive during the brief cosmological window in which the universe is still fully visible to itself. We exist in the universe's one great era of self-awareness, the epoch when matter organized itself into minds curious enough to look outward and read the story of everything. The islands of light are already drifting apart, the darkness between them is already growing. But tonight, right now, the sky is still full. Tonight, all 2 trillion galaxies are still out there, still glowing, still sending their ancient light across the expanding dark toward anyone willing to look up and receive it. That is not nothing. That, in a universe trending towards silence and isolation, is everything. Let me ask you something. When you stand at the shore of an ocean and look out at the horizon, do you believe the ocean ends there? Of course not. You know the water continues beyond what your eyes can reach. You know there are other continents, other shorelines, other people standing on other beaches looking back in your direction, their own horizon cutting off their view just as yours cuts off yours. The horizon is a limit of perception, not a limit of existence. You carry this understanding so naturally that you never question it. You never look at the ocean horizon and think, that is where the water stops. You think, that is as far as I can see. Now I want you to apply exactly that same understanding to the universe. The edge of the observable universe, that 46.5 billion light-year boundary we have been circling tonight, is our horizon. It is as far as we can see. It is emphatically, definitively, not where the universe stops. Beyond it, the cosmos continues. The question that has occupied cosmologists for decades, and that has no clean answer yet, is simply this. How much further does it go? The honest answer is that we do not know. We cannot know, at least not with the tools currently available to us, and possibly not ever. The region beyond our observable horizon is, by definition, causally disconnected from us. No information from that region has had time to reach us. No light, no gravitational waves, no signal of any kind originating beyond our horizon can have arrived at Earth, because the universe has not existed long enough for such signals to make the crossing. We are, in the most rigorous scientific sense, blind to what lies beyond that boundary. But blindness is not the same as ignorance. We can reason about what is likely to be out there, based on the physics we understand, the measurements we have made of the observable universe, and the mathematical models that best fit the data we have collected. And what that reasoning tells us is both humbling and staggering in equal measure. Our best current cosmological measurements suggest that the universe is geometrically flat. This is not a statement about the universe being two-dimensional. It is a statement about the curvature of space on the larger scales. In the geometry of the cosmos, flatness means that parallel lines stay parallel forever, that the angles of a triangle add up to exactly 180 degrees, and that space does not curve back on itself the way the surface of a sphere does. The significance of this flatness for our question tonight is profound. A perfectly flat universe, extended in all directions without boundary or curvature, would be infinite in extent. It would go on forever. And if it is infinite, then everything we can observe, all 2 trillion galaxies, all the cosmic web, all the ancient light of the microwave background is a finite sample drawn from an infinite whole. Our observable universe would be to the total universe what a single cup of water is to all the oceans of the Earth. Except that analogy still does not capture it, because the oceans are finite, and the universe, in this picture, is not. But even setting aside the question of infinity, the total universe is almost certainly vastly larger than the observable portion, regardless of whether it is strictly infinite or merely enormously finite. Here is why. The observable universe looks remarkably uniform at the larger scales. The cosmic microwave background is smooth to 1 part in 100,000 across the entire sky. The distribution of galaxies and galaxy clusters is statistically similar in every direction we look. This uniformity is predicted by a theory called cosmic inflation, the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent an episode of extraordinarily rapid exponential expansion, stretching a region of space far smaller than a proton to a size larger than what we can observe today, in a time so brief it makes a billionth of a second seem leisurely. Inflation explains the smoothness of the CMB, it explains the flatness of the universe. And it predicts that the total size of the universe is almost incomprehensibly larger than our observable bubble. Current estimates from inflationary models suggest the total universe may be at least 10 to the power of 23 times larger than our observable portion. That is a 1 followed by 23 zeros. If the observable universe were a single atom, the total universe would be larger than the observable universe itself. The numbers collapse under their own weight and become impossible to hold. And here is where it becomes truly strange. If the universe beyond our horizon is that large, and if it is filled with matter distributed in the same way matter is distributed in our observable bubble, then somewhere out there, the combinations of particles repeat. There are only a finite number of ways that the particles in a region of space can be arranged. The number is enormous, incomprehensibly so, but it is finite. In a universe large enough or infinite enough, every possible arrangement of matter must occur, not just similar arrangements, identical ones, which means that somewhere beyond our observable horizon, at a distance so vast it has no meaningful name, there is a region of space arranged exactly like the one you are in right now. The same stars, the same planets, the same galaxy, the same solar system, the same Earth. And on that Earth, someone identical to you is lying in the dark, listening to these same words, thinking these same thoughts at this same moment. Not a copy, not a simulation, a genuine physical duplicate, produced not by any exotic mechanism, but simply by the mathematics of large numbers applied to a universe big enough to run every possible configuration of matter at least once. This idea is not science fiction. It is a serious, peer-reviewed prediction of standard inflationary cosmology, discussed openly by physicists including Max Tegmark of MIT, and others who work on the foundations of cosmological theory. It makes many people deeply uncomfortable because it seems to violate our sense of uniqueness, our feeling that this specific arrangement of matter, this particular life, this exact moment of awareness, is singular and irreplaceable. And in the context of our observable universe, it is. There is only one you within the 46.5 billion light-year sphere we can observe. But in the full extent of the cosmos, if the numbers are what the physics suggest they are, uniqueness may be an illusion produced by the smallness of our horizon, not a feature of reality itself. The universe beyond our view is large enough to contain multitudes, large enough, in the most literal mathematical sense, to contain everything. I want to be clear about what we do and do not know here. We cannot confirm any of this directly. We cannot observe beyond our horizon. We cannot test whether the universe is truly infinite or merely very large. We cannot verify the existence of distant duplicates. These are predictions that follow from our best physical models, but they are predictions that in principle can never be directly confirmed, because the evidence for or against them lies permanently beyond our causal reach. What we can say with confidence is that the observable universe is almost certainly not the whole universe, that the cosmos extends beyond our horizon in ways we cannot fully map or measure, that the portion of reality available to our instruments is a sample, possibly a vanishingly small one, of a larger whole whose extent we can reason about but never directly see, and that sitting with that uncertainty, letting it be large and unresolved and genuinely open, is not a failure of knowledge. It is the beginning of wisdom. The universe beyond our view is not empty simply because we cannot see it. It is full and vast and real. And tonight, as you rest here at the center of your own small observable bubble, it stretches away from you in every direction, silent and enormous and indifferent and breathtaking, further than any thought can follow. There is a question that has haunted human beings since the first time someone looked up at the night sky and felt the weight of what they were seeing. It is not a new question. The ancient Greeks argued about it. Medieval philosophers built elaborate theological frameworks to contain it. Mathematicians have wrestled with its implications for centuries, and today, with all the precision instruments and satellite telescopes and supercomputer simulations available to modern cosmology, we are still sitting with it, still turning it over, still unable to give a definitive answer. The question is simply this: does the universe go on forever, or does it end? Is space infinite, or does it have some boundary, some total extent beyond which there is nothing more? It sounds like the kind of question that should have an answer by now. It does not. And the reason it does not is not a failure of science, but a fundamental feature of the universe itself, a cosmic boundary on what any observer embedded inside a finite observable region can ever determine about the whole. To approach this question properly, we need to think about geometry. Not the geometry of triangles on a flat page, but the geometry of space itself, the way the fabric of the cosmos curves or does not curve on the very largest scales. General relativity, Einstein's theory of gravity, tells us that matter and energy cause space to curve. The sun curves the space around it, and that curvature is what we experience as the gravitational pull that keeps Earth in orbit. But on the scale of the entire universe, the average distribution of matter and energy determines the overall geometry of space as a whole. And there are essentially three possibilities for what that overall geometry might be. Each one has profound implications for whether the universe is finite or infinite, and for what it would mean to reach its edge. The first possibility is that the universe has positive curvature. Think of the surface of a sphere. On a sphere, if you travel in a straight line for long enough, you eventually return to your starting point. Parallel lines eventually converge. The angles of a triangle add up to more than 180 degrees. A universe with positive curvature would behave similarly in 3 dimensions. It would be finite but unbounded, meaning it would have a definite total size but no edge, no wall, no boundary you could reach. If you travelled through it in a straight line for long enough, you would eventually return to where you started, the same way a traveller circumnavigating the Earth arrives back at their departure point. This kind of universe has a total volume, a definite amount of space, but no centre and no edge. You could never reach the end of it, not because it is infinite, but because it curves back on itself. The second possibility is that the universe has negative curvature, shaped something like a saddle or a hyperbolic surface that curves away from itself in every direction. In a negatively curved universe, parallel lines diverge, triangles have angles that sum to less than 180 degrees, and the geometry is stranger and harder to visualize than either of the other two cases. A negatively curved universe would be infinite in extent, though its infinite nature would manifest differently than in the flat case. It would go on forever in a space that expands faster than Euclidean geometry would predict. There is no edge in a negatively curved infinite universe. There is simply more space, curving away in every direction, with no terminus and no boundary and no place where the cosmos decides to stop. The third possibility, and the one that our best current observations most strongly support, is that the universe is flat. Precisely, geometrically flat, in the sense that parallel lines remain parallel forever, triangles have angles summing to exactly 180 degrees, and space does not curve in any direction on the larger scales. A flat universe is consistent with being infinite. It does not have to be infinite. A flat universe could still be finite if it has a particular topology, a way of connecting to itself like a 3-dimensional version of a video game screen where you exit on the right and reappear on the left. But the simplest and most natural interpretation of a flat universe is that it is infinite in extent, going on and on in every direction without limit or end. Our measurements of the cosmic microwave background, particularly the detailed maps produced by the Planck satellite, place the curvature of the universe so close to perfectly flat that any deviation from flatness must be smaller than one part in several hundred. The universe, as best we can measure, is flat to extraordinary precision, and if it is truly flat, it is almost certainly infinite. But here is the thing most people do not realize about this measurement, and it matters enormously for our question tonight. When we measure the flatness of the universe, we are measuring the curvature of our observable portion. We are measuring the geometry of that 46.5 billion light-year sphere we can detect. And just as a small patch of the Earth's surface looks flat even though the Earth is a sphere, our observable universe could appear flat even if the total universe curves back on itself on scales far larger than our horizon. If the total universe is at least a few times larger than the observable universe, the curvature would be too gentle for us to detect within our observable patch. We would measure flatness and conclude infinity, when in reality the universe might be finite and spherical, but simply so large that the curvature is below our threshold of detection. The flatness we measure is real, but it cannot distinguish between a truly infinite universe and a finite universe so vast that it appears infinite from where we sit. This is the epistemological wall at the heart of the question. The totality of the universe, whether it is finite or infinite, whether it curves back on itself or extends without limit, lies beyond our observational reach. We can measure our patch. We can extrapolate from our patch. We can build models consistent with our measurements. But we cannot step outside the observable universe to measure the whole. We are like an ant on the surface of the Earth trying to determine whether the Earth is round or flat without ever being able to see more than a few inches in any direction. The ant can measure the local curvature of the ground beneath it, but the resolution of that measurement may be too coarse to detect the gentle, overall curve of the entire planet. We are that ant. Our telescopes are extraordinarily powerful, but the universe may be so much larger than our observable horizon that the curvature, if any, is simply too subtle to detect within our limited view. What I find most striking about this situation is not the uncertainty itself, but the nature of that uncertainty. This is not a gap in our knowledge that better instruments will necessarily fill. It is not a problem that a more powerful telescope will solve. It is a fundamental limit built into the structure of the universe, a consequence of the finite speed of light and the finite age of the cosmos. Some questions about the universe may be permanently, structurally unanswerable, not because we are not clever enough, but because the information needed to answer them is on the other side of a horizon that neither we nor any instrument we could build can ever cross. The question of whether the universe is infinite or finite may be one of those questions. It sits at the intersection of physics and philosophy, in the territory where science runs up against its own limits and hands the inquiry back to human wonder. Tonight, as you lie here in the dark, the universe extends in every direction from where you rest. Whether it goes on forever or eventually curves back to meet itself is unknown. Both possibilities are staggering. Both are real candidates for the truth. And both, in their own way, are more than large enough to hold everything that has ever existed, everything that exists now, and everything that ever will. I want to ask you a question that I would like you to hold very gently, because it is the kind of question that, if you push on it too hard, starts to feel like pressing on a bruise. It is a question that philosophers and physicists and theologians have all approached, each from their own direction, each with their own vocabulary, and none of them have come back with a clean answer. The question is this: if the universe is finite, if space itself has some total extent and does not go on forever, what is on the other side of it? What exists beyond the last inch of space? Not more space that we simply cannot see. Not more universe hidden behind a horizon. If the universe is truly finite, if there is a place where space genuinely ends, what is there? What word do you use for the thing that is not space, not time, not energy, not matter, not vacuum, not darkness, not even emptiness? Because emptiness is still a spatial concept, and we have run out of space. This is not a rhetorical question designed to make you feel small. It is a genuine open problem at the frontier of human understanding, and sitting with it honestly is one of the most unusual and important things a mind can do. Let us start by being very precise about what we mean. When physicists talk about the universe being finite, they do not necessarily mean it has an edge in the way a table has an edge, a boundary you could approach and peer over. As we explored when discussing the geometry of the cosmos, A finite universe could be curved and closed, like the three-dimensional analogue of a sphere's surface. In such a universe, you could travel forever in any direction and never reach a wall. You would simply loop back to your starting point, the way a traveller going west eventually arrives back at their departure point, without ever encountering the edge of the Earth. In that scenario, the question of what is beyond the universe does not quite arise in the same way, because there is no beyond in the spatial sense. The universe contains itself. It is its own container. There is no outside to step into, because the geometry of the space curves back before you can find one. But what if the universe is not curved in that convenient self-containing way? What if it is flat and finite and simply stops? What if there is a place, some incomprehensibly distant region of space, where the coordinates of the cosmos run out, where the fabric of space-time reaches its last point and there is nothing further? This is where language begins to fail us, and where I think that failure is itself informative. When we ask what is on the other side of the universe, we are smuggling in a spatial assumption. The word other side implies a somewhere that is adjacent to the edge, a location you could occupy if you just stepped a little further. But if the universe is the totality of space, then there is no location beyond it, because location is a spatial concept, and space has ended. There is no beyond. There is no other side. There is, in the most complete and vertiginous sense of the phrase, nothing at all. And here is where the nothing gets strange. Because when physicists talk about nothing, they do not mean what most people mean by nothing. In ordinary language, nothing means empty space, a vacuum, a room with no furniture and no air, but empty space is still space. It still has geometry. It still has quantum fields threaded through it, still fluctuates with virtual particles popping in and out of existence, still has measurable properties like the speed of light and the constants of physics. That kind of nothing is very much something. The nothing beyond a finite universe, if such a nothing exists, would be something categorically different. Not empty space, not vacuum, not darkness, because darkness is the absence of light in a space that could in principle contain light. It would be the absence of space itself, the absence of time, the absence of the possibility of location, or duration, or sequence, or causality. A state so fundamentally different from anything we experience that the word nothing may not even be adequate to describe it, because nothing, in the way we use the word, still implies a kind of stage on which the absence is occurring. Take away the stage, and language has very little left to offer. Some physicists and philosophers argue that this question is not actually meaningful. They point out that asking what is outside the universe is like asking what is north of the North Pole. North is a direction defined within the coordinate system of the Earth. At the North Pole you have run out of north. There is no more north to go to. The question dissolves not because the answer is too complex to find, but because the question itself assumes a framework that does not apply at that location. Similarly, outside may be a concept that only makes sense within the universe, defined relative to the spatial relationships that space provides. If space ends, outside loses its meaning. The question of what lies beyond the universe may be not unanswerable but meaningless, a grammatically valid sentence pointing at something that cannot exist by definition. This is not a satisfying answer, but it may be the correct one, and there is a certain austere beauty in a question that dissolves rather than resolves, and yet many cosmologists are not comfortable letting the question dissolve quite so easily. Because there are serious theoretical frameworks, particularly those arising from string theory and quantum gravity, that suggest the universe as we know it may be embedded in a higher dimensional structure. In the same way that a two-dimensional surface can exist within a three-dimensional space, our four-dimensional space-time, 3 dimensions of space plus 1 of time, may be a membrane, a brain in the technical language, embedded in a higher dimensional reality sometimes called the bulk. In this picture, there is something beyond our universe in a very literal sense. Not more of our space, but a different kind of space, a higher dimensional embedding structure in which our universe floats like a soap bubble in air. Other brains, other universes, may float in this same bulk, separated from us not by distance in our familiar 3 dimensions, but by position in the extra dimensions we cannot access. This is speculative. It is not yet confirmed by any observation, but it is taken seriously by serious physicists, and it offers one possible answer to the question of what lies beyond our universe. Not nothing, but a higher dimensional something for which we have no direct evidence and no adequate name. There is also the possibility raised by quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole, that the universe did not emerge from nothing in the way we colloquially imagine, a sudden appearance in a pre-existing void. Instead, the universe may have emerged from a quantum fluctuation in a pre-geometric state in which space and time themselves did not yet exist. In this view, the nothing from which the universe came was not empty space, but the absence of space, a condition without geometry or dimension, from which geometry and dimension spontaneously arose through quantum processes. If that is the case, then the nothing beyond a finite universe, if such a nothing exists, might not be a sterile void, but a seething quantum realm of potential, a ground state of pure possibility from which other universes might also arise. The outside of the universe might, in the deepest possible sense, be the place where universes are born. I want to leave you with this tonight, not as a conclusion but as an open door. We do not know what lies beyond the edge of the universe, or whether the universe has an edge in the meaningful sense at all. We have reached the boundary of what our concepts can clearly describe, the place where space runs out of space and language runs out of words. And rather than finding that frightening, I want to invite you to find it clarifying, because at the edge of the universe, at the limit of the knowable, what remains is pure wonder. Not wonder as a feeling of vague awe, but wonder as the active, disciplined, honest acknowledgement that reality is larger than our minds were built to contain. Tonight, as you close your eyes and let sleep come, the universe extends in every direction from where you lie, and somewhere at its edge or in its infinite continuation, the question of what lies beyond waits patiently, as it has always waited, for a mind large enough to hold it. Picture a pot of water just beginning to boil. Before the full rolling boil arrives, something happens near the bottom. Small bubbles form, nucleating at tiny imperfections in the surface, growing from almost nothing, expanding outward and upward through the surrounding liquid. Each bubble is a pocket of a different phase of matter, water vapor instead of liquid water, separated from everything around it by a thin boundary, a membrane of transition between two states of the same substance. The bubble does not ask permission to exist. It does not announce itself. It simply forms because the conditions allow it, expands because the physics demands it, and rises through a medium that does not share its nature. Now I want you to hold that image in your mind, and scale it up by a factor so vast that every number we have used tonight becomes trivially small by comparison. Replace the pot with the entire fabric of space itself. Replace the surrounding liquid with a state of reality called the false vacuum, and replace each small rising bubble with an entire universe. This is the picture that emerges from one of the most serious and carefully developed frameworks in modern theoretical physics, and if it is correct, it changes everything about how we understand the edge of the universe and what lies beyond it. The theory is called eternal inflation, and its roots go back to the early 1980s, when physicists Alan Guth and Andre Linde were working on the original theory of cosmic inflation. Inflation was proposed to explain several features of our observable universe that were otherwise deeply puzzling. Why is the universe so smooth and uniform in every direction? Why is space so precisely flat? Why does the cosmic microwave background look almost identical no matter which way we point our instruments? The answer inflation proposed was elegant. In the first tiny fraction of a second after the Big Bang, the universe underwent an episode of extraordinarily rapid exponential expansion, stretching a region far smaller than a proton to a size larger than what we can observe today, smoothing out any irregularities the way stretching a wrinkled cloth pulls it flat. Inflation solved the problems beautifully. But when physicists looked carefully at the mathematics of how inflation ends, they discovered something they had not expected. In most models, inflation does not end everywhere at once. It ends locally, in patches, the way ice crystallizes on a cold window, spreading from nucleation points while the surrounding glass remains liquid. Where inflation ends, matter and radiation form, and a universe like ours takes shape. But in the regions between those patches, inflation does not stop. It keeps going. It produces more space, faster than any local ending of inflation can consume it. The inflating background expands so rapidly that even as new patches of ended inflation form and grow, the total volume of still inflating space increases. Inflation, once started in this kind of model, never fully stops. It is eternal. It goes on producing new pockets of ended inflation indefinitely, each one a universe unto itself, forever embedded in a background that never settles. The result of eternal inflation is a structure physicists call the multiverse, though that word carries many meanings and deserves some care. In this specific context, the multiverse is a single vast space-time, eternally inflating, within which bubble universes form continuously, like those bubbles in the boiling pot. Each bubble is a region where the false vacuum has transitioned to a lower energy state, where inflation has ended, where matter and physics as we know them can exist. Our universe is one such bubble, born approximately 13.8 billion years ago from a quantum fluctuation in the inflating background, expanding ever since, carrying within it 2 trillion galaxies and ancient light and dark energy, and every form of matter and life that has ever existed within our cosmic horizon. The walls of our bubble, the actual physical boundary of our universe, are expanding outward in every direction at very close to the speed of light. Beyond those walls is not more of our universe, not more space of the kind we inhabit, but the false vacuum itself, still inflating, still seething with the energy of a space that has never settled into the lower state that allows ordinary matter to exist. Here is what makes this picture genuinely vertiginous. Each bubble universe that nucleates in the eternal inflation scenario need not emerge with the same physical laws as ours. The quantum process of nucleation, the transition from false vacuum to true vacuum, can in principle produce different outcomes in different bubbles, different values for the fundamental constants of nature, a different strength of gravity, a different mass for the electron, a different relationship between the forces that hold atoms together. In our universe, these constants are tuned to values that allow stars to form, atoms to stabilize, chemistry to occur, and life to arise. Change most of them even slightly, and the universe becomes sterile in one way or another, either collapsing before the first star ignites, or expanding so fast that matter never has time to clump into anything interesting. In the eternal inflation multiverse, other bubbles may have formed with constants incompatible with complexity of any kind. Universes that burned bright and died in seconds, or expanded into endless cold without ever forming a single star. And some bubbles, statistically rare but not impossible, may have constants different from ours yet still compatible with some form of organized complexity we cannot imagine from inside our own particular bubble. The wall of our bubble is one of the most extraordinary objects that physics has ever been forced to contemplate. It is the true edge of our universe, not the edge of the observable portion, not the cosmic event horizon, not the wall of ancient microwave light, but the actual physical boundary of the space-time we inhabit, the membrane separating our reality from the inflating exterior. That wall is expanding outward right now, moving away from every point in our universe at very close to the speed of light. It will never stop expanding. It will never be reachable from the inside because it is moving away faster than anything inside our bubble can travel. We are permanently interior to our bubble, the same way a sound wave is permanently interior to the air it travels through, unable to step outside its own medium. But the wall is real. It exists. And if 2 bubbles expanding through the inflating background ever grew large enough to make contact, their walls would collide. Not the interiors, not the galaxies and stars within each bubble, but the expanding shells themselves, those thin membranes of transitioning vacuum energy meeting and interacting at the boundary where 2 separate universes touch. A collision between 2 bubble universes would not be subtle. The impact would send a shock wave propagating inward through each colliding bubble at the speed of light, a disturbance moving through the interior of our universe, altering the distribution of matter and energy along a circular boundary on the sky. Such a collision, if it occurred in the early history of our universe, would leave a mark, a scar. A circular anomaly in the oldest light we can detect, the cosmic microwave background, where the temperature and polarization of that ancient radiation would differ in a distinctive pattern from the surrounding sky. Several physicists have taken this prediction seriously enough to look for it. They have combed through detailed maps of the CMB produced by satellites like WMAP and Planck, searching for circular features that might indicate the edge of a bubble collision, a bruise left on our universe by contact with another. Some unusual features have been noted, none has been definitively confirmed as a bubble collision signature. The search continues, because if such a signal were ever conclusively identified, it would be the first direct observational evidence that our universe is not alone, that other realities exist beyond our walls, and that the multiverse is not merely a theoretical framework, but a measurable feature of reality. Let that settle into you slowly, the way the quiet of late night settles into a room. We may be living inside a bubble. A nucleation event that occurred 13.8 billion years ago produced a pocket of space where the laws of physics allow matter and complexity and awareness to exist, and that pocket has been expanding ever since, its walls racing outward through an inflating background we can never reach or observe. Beyond our walls, other bubbles are forming, other universes are unfolding, other configurations of physics are playing out in conditions so alien we have no sensory framework for imagining them. We are inside something. We have always been inside something. And the something we are inside, this universe, with all its terrifying scale and ancient light and dark energy and unanswered questions, is itself contained within something larger still. Tonight, as your breathing slows and the edges of the day soften into sleep, carry that image with you. A bubble, rising through an eternal sea, the edge of everything you can know, racing outward at the speed of light, and beyond it, possibility without end. There is a particular kind of silence that comes after a collision. Not the silence of emptiness, but the silence of aftermath, of energy dispersed, of two things that were separate now permanently changed by their contact. You know this silence intuitively. You have felt it after a door slams in a quiet house, after a glass breaks on a tile floor, after thunder rolls away across a night sky. The collision announces itself, and then the world reassembles around what has changed. Now I want you to imagine a collision on the most extreme scale that physics allows. Not two cars, not two planets, not even two stars, two universes. Two bubble universes, each one containing billions of galaxies and trillions of stars, each one expanding outward through the eternal inflating background at close to the speed of light, growing for billions of years in their separate spacetimes until the expanding walls of one brush against the expanding walls of the other. The contact would last an instant in cosmic terms. The shockwave from that contact would travel inward through each universe at the speed of light, a ring of disturbance expanding across the sky of every world within reach, leaving behind it a permanent scar on the fabric of space, encoded in the distribution of matter and the temperature of ancient light. And here is the most extraordinary part of this picture. We might already be looking at that scar. It might be sitting in our data right now, waiting to be recognized for what it is. To understand how physicists search for evidence of bubble collisions, you need to return to the cosmic microwave background one more time. We have visited that ancient wall of light several times tonight, and each time it has revealed something new about the nature of the universe and its boundaries. The CMB is the oldest electromagnetic signal we can detect, the afterglow of the moment the universe became transparent, imprinted with the conditions of the cosmos 380,000 years after the Big Bang. Its temperature is almost perfectly uniform across the sky, varying by only tiny fractions of a degree from one direction to another. Those tiny variations, those subtle ripples in the ancient light, carry information about the earliest moments of cosmic history, about the distribution of matter in the infant universe, about the physics of inflation and the seeds of the large-scale structure we observe today. Cosmologists have mapped these temperature variations in extraordinary detail, first with the COBE satellite in the early 1990s, then with WMAP, and most recently with the Planck satellite, which produced the most precise full-sky map of the CMB ever made. What they found confirmed the standard model of cosmology with remarkable precision. But it also revealed a handful of features that were unexpected, features that do not fit neatly into the simplest versions of inflationary theory, features that some physicists believe might be pointing towards something genuinely new. The most discussed of these anomalies is something called the cold spot. Located in the southern sky, in the constellation Eridanus, the CMB cold spot is a region significantly cooler than the average temperature of the background radiation, larger and colder than standard inflationary models predict should be possible by chance. Its existence was confirmed by multiple independent analyses of the WMAP and Planck data. Several explanations have been proposed. Some researchers suggest it could be the result of a supervoid, an enormous region of space containing far less matter than average, through which the ancient light passed and lost energy on its way to our detectors. Others have proposed that it might be a statistical fluctuation, unlikely but not impossible given the vast number of possible CMB patterns. And a smaller but serious group of physicists has suggested that the cold spot might be the signature of exactly what we have been discussing tonight, a collision between our bubble universe and a neighbouring one, a circular imprint left on the CMB by the shockwave from a contact event billions of years ago, when the wall of our universe brushed against the wall of another reality, expanding through the same inflating background. The predicted signature of a bubble collision in the CMB is specific enough to be testable, which is one of the things that makes this hypothesis scientifically serious rather than merely speculative. When two bubble universes collide, the wall of our bubble is displaced in the region of contact, and a shockwave propagates inward through our universe. That shockwave would leave a distinctive mark on the CMB, a circular or elliptical feature with a sharp edge, in which the temperature and polarization of the ancient light differ in a specific calculable way from the surrounding sky. The boundary of the feature should be abrupt, not gradual, because the shockwave from the collision moves at the speed of light and creates a clean edge between affected and unaffected regions. Researchers have developed detailed mathematical models of what such a signature should look like, and have searched systematically through CMB maps for features matching those predictions. The cold spot in Eridanus matches some but not all of the predicted characteristics. It is circular. It is anomalously cold. Its edges are somewhat sharper than pure statistical fluctuations typically produce, but the polarization signature that would most convincingly confirm a bubble collision has not been definitively detected, and alternative explanations remain viable. The case is open. The jury is still deliberating. What I find remarkable about this search is not its current inconclusiveness, but its sheer audacity. Human beings living on a small rocky world orbiting an ordinary star in one spiral arm of one galaxy, among 2 trillion, have developed instruments sensitive enough to detect temperature variations of millionths of a degree in 13-billion-year-old light, and are using those measurements to search for evidence of contact with another universe. We are looking for a scar left by a collision between realities. We are trying to read, in the oldest light we can detect, the mark of something that exists beyond the edge of everything we know. The fact that we can even formulate this question precisely enough to search for an answer is one of the most extraordinary things about human science. We are not just inhabitants of our bubble. We are investigators of its history, detectives searching for clues about what our universe has touched and what has touched it, using instruments of almost incomprehensible delicacy to peer at the boundary between the known and the genuinely unknowable. There is another consequence of bubble collisions that deserves a moment of attention because it speaks directly to the question of what lies beyond our edge. If our universe has collided with another bubble, then that other bubble is real. Not real in the sense of being a mathematical abstraction or a theoretical convenience. Real in the sense of being a physical space-time containing whatever it contains, governed by whatever physics its nucleation produced, expanding outward through the same eternal inflating background that our universe expands through. A confirmed bubble collision signature in the CMB would be the first observational evidence that our universe is not the only universe, that the multiverse is not merely an elegant theoretical framework, but a measurable feature of the physical world. It would be, without exaggeration, the most significant scientific discovery in human history. It would expand our concept of reality in the same way that the discovery of other galaxies beyond the Milky Way expanded our concept of the cosmos in the early 20th century, revealing that what we had taken to be the whole was merely one instance of something far larger and more varied than we had imagined. And yet, even without confirmation, the search itself changes something. The fact that we are looking, that we have developed the tools and the theories to look, that we have identified specific, testable predictions that would distinguish a universe collision scar from ordinary statistical noise means that the question of what lies beyond our edge has moved from pure philosophy into the domain of empirical science. We are not just asking whether other universes exist. We are checking the data. We are running the tests. We are holding the ancient light of our universe up to the light of reason and asking it very carefully whether it carries the memory of a touch from something outside itself. Tonight, as you rest here in the dark, that search is ongoing. The data from the Planck satellite still sits in the archives, being reanalyzed with new methods and new eyes. The next generation of CMB telescopes is being planned and built with sensitivity that will dwarf anything we have flown before. And somewhere in that data, or in the data yet to come, there may be a circle drawn in ancient light, the signature of a moment when two universes met at the edge of everything, and one of them left a mark on the other that we are only now learning to read. Every story has an ending, even the longest ones, even the ones that feel, from inside, as though they could go on forever. The universe is the longest story there is, 13.8 billion years already written, with a future stretching ahead that dwarfs even that enormous past by incomprehensible factors. But the universe has an ending, not a wall it runs into, not a boundary it reaches, an ending written into its own physics, encoded in the laws of thermodynamics and the relentless logic of entropy, playing out across timescales so vast that every number we have used tonight begins to feel almost quaint by comparison. Tonight, I want to walk with you to that ending, slowly, quietly. The way you might walk to the edge of a great cliff at dusk, not to jump, not even to look down, but simply to stand at the boundary between something and what comes after it, and let the scale of what you are witnessing settle into your bones. The death of the universe is not a violent thing. It is not an explosion or a collapse or a sudden catastrophe. It is something far more serene, far more patient, and in its own way, far more beautiful than any ending we might have imagined. Let us begin with the stars, because the stars are where most of the universe's visible story is written. Right now, across the 2 trillion galaxies in our observable universe, stars are being born by the billions. Clouds of hydrogen gas collapse under gravity, heat up at their cores, ignite nuclear fusion, and begin the long, slow burn that will define their lives for millions or billions or trillions of years depending on their mass. Our own sun is roughly halfway through its 10 billion year main sequence lifetime. It has been burning for 4.6 billion years and has approximately another 5 billion to go before it exhausts its hydrogen fuel and expands into a red giant, swallowing Mercury and Venus and possibly Earth before eventually shedding its outer layers and collapsing into a slowly cooling white dwarf. That is the fate of most stars: a long burn, a dramatic late phase, and then a quiet, cooling remnant drifting through space for eternity. But what happens when the last star forms? What happens when the universe has used up all the hydrogen available for star formation and no new stars can ignite? That moment is called the end of the stelliferous era, the age of stars, and it arrives in roughly 100 trillion years, one followed by 14 zeros. The universe will have been burning stars for about 7,000 times longer than it has already existed when that final star flickers to life and begins its own slow countdown to darkness. After the last star dies, the universe enters a phase cosmologists call the degenerate era. The galaxies of the future, by this point long since isolated from one another by the accelerating expansion we have discussed, will be populated not by burning stars but by their remnants. White dwarfs, the dense cooling cores of sun-like stars, slowly radiating their remaining heat into the surrounding dark over timescales of quadrillions of years. Neutron stars, the crushed remnants of more massive stars, spinning down from their initial rapid rotations over billions of years. And black holes, the most extreme objects the universe produces, the collapsed remnants of the most massive stars and the supermassive engines at the centers of galaxies, which will become the dominant structures of the universe in the deep future simply by outlasting everything else. During the degenerate era, the universe grows steadily darker and colder. The white dwarfs cool toward absolute zero over timescales that make the current age of the universe look like a heartbeat. Occasional events punctuate the darkness. Proton decay, if protons are not perfectly stable as some theories predict, will slowly disintegrate the matter in white dwarfs and neutron stars, releasing faint bursts of energy that briefly light the darkness before fading again. Random quantum tunneling events will occasionally cause rogue planets and stellar remnants to fall together and ignite brief fusion reactions. But these are sparks in an overwhelming dark, rare and brief, and separated by silences of incomprehensible duration. And then there are the black holes. In the era after all other structures have faded, black holes will be the last significant objects in the universe. They will have grown enormous by this point, having consumed whatever matter drifted close enough to fall within their gravitational reach over the preceding unimaginable spans of time. The largest ones, the supermassive black holes at the centres of what were once galaxy clusters, will contain the mass of billions of suns compressed into a region smaller than our solar system. They will drift through the darkness like vast silent monuments, the last complex structures remaining in a universe that has otherwise smoothed itself toward uniformity, and even they will not last forever. In 1974, the physicist Stephen Hawking made one of the most remarkable theoretical predictions in the history of science. He showed that black holes are not perfectly black. Quantum mechanical effects near the event horizon cause them to emit a faint thermal radiation, now called Hawking radiation, losing mass and energy at an extraordinarily slow rate. A black hole the mass of our Sun would take 10 to the power of 67 years to evaporate completely through Hawking radiation. A supermassive black hole containing the mass of 1 billion suns would take approximately 10 to the power of 96 years. These numbers are not just large. They are large in a way that defeats imagination entirely, but they are finite. Every black hole will eventually evaporate. Every last complex structure in the universe will eventually dissolve into a thin mist of photons and fundamental particles, spreading outward into an ever larger and ever emptier space. What remains after the last black hole evaporates is what physicists call heat death, or the maximum entropy state of the universe. It is not a dramatic ending. There is no explosion, no collapse, no final moment of violence. There is simply a universe that has become as disordered as it is possible to be, in which energy is distributed so uniformly across such an enormous volume of space that no further work can be extracted from it. No temperature difference remains to drive any process, no structure forms, no event occurs. The universe does not end in heat death in the sense of reaching a wall or a boundary. It simply reaches a state of perfect eternal stillness, a cosmic equilibrium so complete that even the passage of time becomes meaningless, because time, in the physical sense, is defined by change, and in a universe where nothing ever changes, time has nowhere left to go. The universe in heat death is not dead in any dramatic sense. It simply is, in the most minimal and featureless way that something can be, stretched across a volume of space incomparably larger than the one we inhabit tonight, cold beyond any cold we can describe, dark beyond any dark we can imagine, and utterly, perfectly, endlessly still. I want to sit with you for a moment in that stillness, not with dread, not with the impulse to turn away from it and reach for something more comfortable, but with genuine, open attention, because the ending of the universe, that long, slow fade from a cosmos of blazing stars and rushing galaxies to a cold and featureless dark, is not a tragedy. It is the completion of a story that began with a quantum fluctuation in conditions we cannot fully describe and will end with the last photon of Hawking radiation dissolving into a space so vast that the photon's energy is spread across a volume larger than anything we have words for. Every star that ever burned, every planet that ever formed, every molecule that ever assembled into something capable of awareness and wonder, every thought that was ever thought about the nature of space and time and the edges of the universe, will have been part of that story, will have been, in the most literal sense, what the story was about. The universe did not create itself in order to end in darkness, but it will end in darkness, after a story so long and so full that the darkness, when it finally comes, will feel less like loss and more like rest. Tonight the story is still being written, the stars are still burning, the galaxies are still rushing outward, the ancient light is still crossing the dark, and you are here, awake enough to know it, at this particular and unrepeatable moment in the longest story ever told. I want to bring us back for a moment from the vast and the abstract. We have travelled tonight to the edge of the observable universe, stood at the wall of ancient light, contemplated the accelerating expansion and the fate of bubble universes and the heat death of everything. We have handled distances and timescales that dissolve the ordinary mind, and now I want to come back to something immediate, something you can feel right now, in this moment, as you lie here in the dark. I want to talk about you, not you as a philosophical abstraction, not you as an observer in a cosmological model, but you as a physical object. a collection of matter sitting in a specific place on a specific planet at a specific moment in the history of the universe. Because here is the thing most people never fully reckon with. The matter you are made of is ancient, profoundly, almost incomprehensibly ancient, and its history connect you, physically and directly, to the very edges and origins of the universe we have been exploring tonight. Every atom in your body has a history, not a metaphorical history, a literal, traceable, physical history that stretches back billions of years and passes through some of the most extreme environments the universe has ever produced. The hydrogen atoms in the water inside your cells, the simplest and most abundant element in the cosmos, were forged in the first 3 minutes after the Big Bang, when the universe was hot enough and dense enough for protons and neutrons to fuse into the nuclei of the lightest elements. Those hydrogen nuclei, those single protons, have existed for 13.8 billion years. They were present in the early universe when the first stars formed from vast collapsing clouds of primordial gas. They have been part of stars and nebulae and interstellar clouds and comets and oceans and living cells across billions of years of cosmic and planetary history. The hydrogen in your body is as old as the universe itself. It was here before the Earth existed, before the sun ignited, before the Milky Way had taken its current shape. It is the oldest thing you will ever touch, and you are made of it. The heavier elements in your body have an even more dramatic origin story. Carbon, the backbone of every organic molecule in every living thing on Earth. Oxygen, which you breathe, and which makes up the majority of your body's mass by weight. Nitrogen, iron, calcium, phosphorus, all the elements that build your bones and blood and neurons, and the intricate molecular machinery of your cells. None of these elements existed in the early universe. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything heavier had to be made somewhere, by some process, before it could become part of you. That somewhere was the cause of stars. Inside a star, the pressure and temperature at the core are extreme enough to force atomic nuclei together, fusing lighter elements into heavier ones and releasing the energy that makes the star shine. Stars are nuclear furnaces, spending their entire lives converting hydrogen into helium, and then, in their later stages, forging heavier elements up to iron in a cascade of nuclear reactions that builds the periodic table from within. The carbon in your DNA was made inside a star. The oxygen in your lungs was made inside a star. The iron in your blood was made inside a star, in the most energetic nuclear reactions that stellar cores can sustain. But stars, as we have discussed, do not live forever, and when a massive star reaches the end of its life, it does not simply go dark, it explodes. In a supernova, one of the most violent events in the universe, the outer layers of a dying massive star are blasted outward at a significant fraction of the speed of light, carrying with them all the heavy elements forged in the star's core over millions of years of burning. The explosion seeds the surrounding region of space with carbon and oxygen and iron and dozens of other elements, enriching the interstellar gas and dust with the raw materials for planets and chemistry and life. Our solar system formed about 4.6 billion years ago from one such enriched cloud of interstellar gas and dust, a cloud that had been seeded by the deaths of multiple previous generations of stars over billions of years of galactic history. The heavy elements in your body passed through at least one, and probably several, stellar deaths before they became part of the cloud that collapsed to form the sun and its planets. You're not just made of star stuff, as Carl Sagan famously said. You're made of the ashes of dead stars scattered across space by explosions of incomprehensible violence, drifting through the galaxy for billions of years before the gravity of a forming solar system gathered them, and the slow processes of planetary and biological evolution assembled them into the particular and improbable arrangement that is you. And here is where this connects back to everything we have been exploring tonight. The edges of the universe, the cosmic horizon, the wall of ancient light, the inflating background beyond our bubble, all of these are not separate from you. They are part of the same story. The matter in your body originated in a universe that has been expanding since the Big Bang, cooling from the unimaginable heat of creation, forming structures at every scale from the cosmic web down to the atom. The hydrogen in your cells is a relic of the first minutes of cosmic history, a survivor of the hot, dense plasma that filled all of space before the first star ever formed. The heavier elements in your body are products of stellar nucleosynthesis, the universe's mechanism for building complexity out of simplicity, for taking the simple hydrogen of the Big Bang and running it through billions of years of stellar evolution to produce the rich periodic table of elements that chemistry and biology require. You're not separate from the universe. You're a local, temporary, highly organized expression of it, a place where the universe has gathered some of its matter into a configuration complex enough to look back at itself and wonder. This is worth sitting with very slowly, because when we talk about the edge of the universe, about the cosmic horizon and what lies beyond it, we are not talking about something remote and irrelevant to ordinary human experience. We are talking about the context in which your atoms have existed for their entire history. The universe that has an edge and an expanding wall, and a future of increasing isolation and eventual heat death, is the same universe that made you. Every atom in your body has been on a journey of billions of years, passing through stellar cores and supernova explosions and interstellar clouds, and planetary formation and biological evolution before arriving, in this moment, in the arrangement that constitutes your awareness. The scale of that journey, from the first minutes after the Big Bang to this particular night, to your particular body lying in this particular dark, is the same scale we have been exploring all evening. The cosmic and the personal are not different scales of the same story. They are the same scale. You're as old as the universe, in the only sense that matters physically. Your matter is. The you that is aware of all this is new. But the stuff you are made of has been here since nearly the beginning. There is a question I want to leave with you as we move toward the final chapters of tonight's journey. When you look up at the night sky and see the distant galaxies, or when you contemplate the edge of the observable universe and the darkness beyond it, you're not looking at something outside yourself. You're looking at more of what you're made of. The same atoms, the same fundamental particles, the same quantum fields that constitute your body constitute every star and galaxy in the observable universe, and presumably everything beyond the horizon we cannot see. The edge of the universe is not the edge of something foreign and alien. It is the edge of the extended community of matter to which you belong, the far shore of the sea of atoms and energy that includes everything from the hydrogen in your cells to the most distant quasar we have ever detected. Tonight, as you breathe slowly in the dark, the universe breathes with you. Its matter is your matter. Its history is your history. Its edges are, in the deepest possible sense, your edges too. There is a particular quality to the silence at the edge of things, not the silence of a quiet room, which is still full of the hum of electricity and the sound of your own breathing and the distant rumour of the world outside, not the silence of a forest at night, which is alive with insects and wind and the soft movements of animals in the dark. I am talking about a different kind of silence, the silence of absolute limit, the silence that exists not because sound has been dampened or absorbed, but because the medium through which sound could travel has come to an end, the silence on the other side of the last boundary. Tonight, I want to sit with you in that silence for a while. Because at the edge of the observable universe, at the cosmic horizon we have been circling all evening, there is a silence of a very specific and very profound kind. It is the silence of information, the silence of a boundary beyond which no message can ever cross, no signal can ever travel, no knowledge can ever be transmitted. It is the silence of the permanently unknowable, and once you understand it fully, it changes the way you think about what it means to know anything at all. Let me be precise about what I mean by the silence at the boundary. Within our observable universe, information travels. Light carries information from distant galaxies to our telescopes. Gravitational waves carry information from colliding black holes across billions of light years to our detectors. The cosmic microwave background carries information from the moment the universe became transparent, 13.8 billion years ago, to our instruments today. All of this information crosses space at the speed of light, the ultimate speed limit of the cosmos, and arrives at our detectors after journeys measured in millions or billions of years. As long as the source of information is within our cosmic event horizon, its signals can in principle reach us, given enough time. The universe within our horizon is, in this sense, a communicating system, not a fast one, not a convenient one, but a connected one, in which events in one place can eventually influence and inform observers in another. Beyond the cosmic event horizon, that changes completely. A galaxy located beyond our horizon, in the region of space that the accelerating expansion has permanently placed outside our causal reach, cannot send us a signal that will ever arrive. Not because the signal would take too long, not because our instruments are not sensitive enough to detect it, but because the space between us and that galaxy is expanding faster than the signal can travel, and will continue expanding faster for the entire infinite future of the universe. The signal, moving at the speed of light, the fastest anything can move through space, is nonetheless losing ground to the expansion of space itself. It will travel forever toward us and never arrive. The galaxy that emitted it might as well not exist, from the perspective of any causal influence on our future. We can see its past light, the light it emitted before it crossed our horizon, light that began its journey when the expansion had not yet placed that galaxy beyond reach. But its present and its future are permanently, structurally inaccessible to us. The silence at the boundary is not the silence of distance. It is the silence of a one-way door, closed forever by the physics of an accelerating universe. Here is what makes this silence genuinely terrifying in the most precise sense of that word. It is not a practical limitation that better technology might overcome. It is not a gap in our knowledge that future generations might fill with cleverness or persistence. It is a fundamental structural feature of the universe we inhabit, built into the relationship between the speed of light, the rate of cosmic expansion, and the infinite future of time. No civilization, no matter how advanced, no matter how long-lived, could ever receive information from beyond the cosmic horizon. The limit is not technological, it is physical. The universe has drawn a line around the domain of the knowable and declared, with the quiet authority of mathematics, that what lies beyond that line is not merely unknown, but permanently, irrevocably unknowable. This is not a failure of science, it is a discovery of science. We have mapped the boundary of knowledge itself, and we have found that it is real and fixed and moving away from us in every direction at very close to the speed of light. Consider what this means for the question of other intelligent civilizations, other minds in the universe, other forms of awareness that might exist beyond our horizon. We have not yet found evidence of any intelligent life beyond Earth within our observable universe, a puzzle known as the Fermi paradox that deserves its own long night of contemplation. But set that aside for a moment and consider a simpler question. Even if intelligent civilizations exist beyond our cosmic horizon, civilizations with technology far beyond ours, civilizations that have been sending signals in every direction for millions of years, those signals can never reach us. The boundary is absolute for them as much as for us. A civilization located just beyond our event horizon, a civilization that might be separated from us by only a few billion light-years more than the accessible limit, is as permanently isolated from us as if it existed in a completely separate universe. We could not call to it. It could not call to us. No exchange of information, no cultural contact, no scientific collaboration, no signal of any kind could ever bridge that gap. The cosmic horizon is the most complete isolation in existence. It makes the loneliness of any earthly solitude feel almost cozy by comparison. And yet, there is something in this silence that I want you to hear differently than you might expect. Because the silence at the boundary is not just a limit, it is also a definition. It defines the shape of what we are. Every observer in the universe, at every location, is surrounded by their own sphere of causal connection, their own bubble of knowability, defined by how far light has had time to travel and by how far the expansion allows information to reach. That sphere is our universe, in the most practical and meaningful sense of the word. Not the mathematical universe, which may be infinite, or may be a bubble in a multiverse. But the universe that matters to us, the universe that can affect us and be affected by us, the universe in which our existence has causal weight. It is the universe defined by the silence at its edge. Everything inside the silence is us. Everything outside it is, in the most complete physical sense, beyond our world. There is a concept in information theory called the event horizon of knowledge, a boundary beyond which no data can be retrieved. We live inside such a horizon. The cosmic event horizon is literally an information horizon, a surface beyond which data cannot cross in our direction. And just as the event horizon of a black hole defines the black hole by marking the boundary of its causal influence, the cosmic event horizon defines our universe by marking the boundary of ours. We are not prisoners of this horizon. We are constituted by it. The silence at the boundary is not the silence of exclusion, but the silence of definition. The quiet that marks the edge of the only world that can ever be ours. Beyond it, the universe continues, vast and indifferent and perhaps populated with wonders we will never know. But inside it, within the sphere of light and causality and ancient radiation that our horizon encloses, there is everything that has ever mattered to any awareness that has ever existed on this small world orbiting this ordinary star. Tonight, as you lie here in the dark, you're inside the largest thing you can ever be inside. You're at the center of your own sphere of knowability, surrounded in every direction by the silence at the boundary, held within a bubble of information and light that is yours, completely and only yours, for the entire duration of your existence. That silence is not empty. It is full of everything the universe has been able to send you across 13.8 billion years of cosmic history. And that, even with all its limits and all its mysteries, is more than enough to fill a lifetime of wonder. Every edge in human history has been a test, not a test of strength or speed or technology, though all of those have mattered in their time, a test of something more fundamental, a test of what a mind does when it reaches the boundary of the known and looks outward into the unknown. Does it turn back? Does it pretend the boundary is not there, or does not matter, or will not hold? Does it freeze in the face of what cannot be mapped or measured or controlled? Or does it do the rarer, harder, stranger thing? Does it stand at the edge, look clearly at what it cannot see, and choose, deliberately and with full awareness of the choice, to remain curious, to remain open, to let the unknown be large and unresolved and genuinely exciting rather than simply terrifying? That choice, made at the edge of every map humans have ever drawn, is perhaps the most distinctly human thing there is. And tonight, at the edge of the universe itself, we're being asked to make it again. Think of the edges that came before this one. There was a time when the edge of the known world was the horizon visible from a hilltop, and the people who chose to walk beyond that horizon rather than turning back were the ones who eventually mapped continents. There was a time when the edge of the known sky was the dome of fixed stars visible to the naked eye, and the people who built telescopes and pointed them upward were the ones who discovered that the sky was not a dome but a depth, that those fixed stars were suns at incomprehensible distances, that the faint smears between the stars were entire galaxies of billions of stars each. There was a time when the edge of the known universe was the Milky Way itself, and the people who argued that those faint spiral nebulae were not gas clouds within our galaxy, but separate island universes far beyond it, were dismissed and then proven right, and then celebrated. Every edge that once felt like the end of everything turned out to be a doorway. Every boundary that once seemed absolute turned out to be a horizon, concealing more universe than anyone had imagined on the other side. The cosmic horizon is different from all those previous edges, and I want to be honest with you about how it is different, because I think that honesty is important. Those earlier edges were practical limits, limits of technology or transportation or imagination, that human ingenuity eventually found ways to cross or see beyond. The cosmic event horizon is not a practical limit. It is a physical one, built into the structure of space-time by the speed of light and the accelerating expansion of the universe. We will not build a telescope powerful enough to see beyond it. We will not develop a propulsion system fast enough to cross it. We will not find a loophole in the physics that lets us sneak a signal past it. The boundary at the edge of our observable universe is, as far as we know, permanent and absolute. In that sense, it is unlike any edge our species has faced before. It is the one edge we cannot cross, the one horizon we cannot walk past, the one unknown we cannot, even in principle, convert into the known. And yet, I do not think this makes the choice to wonder any less important. If anything, I think it makes it more so. Because wonder, real wonder, does not require the possibility of resolution. Real wonder is not the same as curiosity, which hungers for an answer and is satisfied when one arrives. Real wonder is what remains when you know that no answer is coming. It is the capacity to stand at the edge of the permanently unknowable and feel, not frustration or despair, but something closer to reverence. The cosmic horizon asks us to wonder, not because wondering will eventually lead to crossing it, but because wondering is the appropriate response to an existence that includes such things. The universe has given us eyes that can detect light from 13 billion years ago. It has given us minds capable of understanding the geometry of space-time and the physics of black holes and the mathematics of eternal inflation. And then it has placed us inside a bubble with a hard edge and said, "This is as far as the light can reach." What you do with that fact is entirely up to you. Here is what I find most remarkable about the human response to cosmic limits. We have known for decades that the observable universe has a boundary, that there are galaxies beyond our horizon that we can never reach, that the accelerating expansion is carrying more of the cosmos beyond our causal reach with every passing year. And rather than responding to this knowledge with despair or indifference, scientists have responded with extraordinary creativity. They have developed theories of eternal inflation and the multiverse not as fantasies, but as serious mathematical frameworks for reasoning about what might lie beyond the boundary, even without direct observation. They have designed experiments to search for bubble collision signatures in the cosmic microwave background, looking for indirect evidence of realities we can never directly access. They have used the mathematics of quantum cosmology to reason about the conditions before the Big Bang, before time itself existed in any form we recognize. They have pushed the tools of reason and mathematics as far as they will go, not to deny the limits, but to see as clearly as possible, right up to the edge of them. That is not surrender to the unknown. That is the most sophisticated possible engagement with it. And there is something else, something quieter and more personal that I want to offer you as we approach the end of tonight's journey. The cosmic horizon is a limit on what we can know about the universe, but it is not a limit on what we can feel about it. Standing at the edge of the observable cosmos, knowing that the universe extends vastly and unknowably beyond what we can detect, knowing that we inhabit a small bubble of causal connection in an ocean of space that may be infinite, knowing that the atoms in our bodies came from stellar explosions billions of years before the Earth existed, knowing that the ancient light of the cosmic microwave background is the oldest thing we can detect, and that something unimaginably vast and old lies behind it. Knowing all of this does not make us small. It makes us extraordinary. Not because we are at the center of anything. We are not. Not because the universe cares about our existence. It does not. But because we are the part of the universe that knows these things. We are the local, temporary, improbable arrangement of matter that has looked outward and understood its own smallness, and found that smallness magnificent rather than diminishing. The choice to stand at the edge and wonder rather than turning away is not just a scientific choice, it is a human one. It is the same choice that was made by every person who ever looked up at the night sky, with genuine curiosity rather than indifference. Whoever asked why the stars are where they are or what lies beyond the last visible galaxy, or whether the universe goes on forever, or has some final boundary no signal can cross. It is a choice that connects you, tonight, lying here in the dark, to everyone who has ever made it before you. To the ancient astronomers who mapped the stars with the naked eye, to Galileo turning his telescope on the sky for the first time, and finding that the smooth face of the moon was rough and cratered and real, to Edwin Hubble discovering that the universe was expanding and that the cosmos was vaster and stranger than anyone had imagined, to the teams of physicists who found, to their own shock, that the expansion was accelerating and that the future of the universe was darker and more isolated than they had hoped. Each of them stood at an edge. Each of them chose to look, and because they did, you are here tonight, at the greatest edge of all, with all of their accumulated seeing in your hands, looking outward into the permanent dark beyond the last light, and choosing, as they chose, to find it beautiful. We have come a long way tonight. We started here, in this quiet dark, in this room, in this body that breathes and feels and wonders, and we travelled outward, step by step, past the familiar stars and the distant galaxies, past the cosmic web and the wall of ancient microwave light, past the event horizon and the bubble boundary and the eternally inflating sea beyond our universe. We looked at the edge of the observable cosmos and tried, with honest and unhurried attention, to understand what that edge means and what might lie beyond it. We sat with questions that have no clean answers. We held uncertainties that will not resolve in any human lifetime, and now we are coming back. Back to this room, this breath, this moment of stillness at the end of a long journey, through the largest thing the human mind has ever attempted to comprehend. I am glad you stayed with me. I am glad we made this journey together, because the universe, vast and silent and edged with permanent mystery as it is better contemplated in company than alone. Let me gather for you, gently, what we found at the edge. We found that the universe has a boundary, not a wall in space, but a horizon in time, defined by how far light has travelled in 13.8 billion years. We found that beyond that horizon the universe continues, possibly forever, in ways we cannot observe and may never fully reason about. We found that dark energy is accelerating the expansion of space, carrying galaxies beyond our causal reach one by one, reducing the domain of the knowable with every passing billion years. We found that our universe may be a bubble, one nucleation event in an eternally inflating sea of possibility, surrounded by other bubbles carrying other physics in other configurations of reality. We found that the oldest light we can detect, the cosmic microwave background, is both a window onto the earliest moments of cosmic history and a wall that permanently hides what came before. And we found that the matter in your body, the hydrogen and carbon and oxygen and iron that constitute your physical existence, came from the very beginning of all this, forged in the Big Bang and in the cores of dead stars and scattered across space by explosions of incomprehensible violence before gravity and chemistry and biology assembled it into you. The edge of the universe is not remote from you. It is the far shore of the sea you are made of. Here is what I want you to carry from tonight into your sleep and into tomorrow. The universe is unimaginably large, terrifyingly large if you let yourself feel the full weight of the scale. The observable portion alone contains 2 trillion galaxies across 93 billion light-years, and beyond that horizon, the cosmos extends further than any number we have used tonight can describe. It is old beyond reckoning, and it is trending toward a future of increasing isolation and eventual stillness. The edge of the observable universe is moving away from us in every direction, carrying more of reality beyond our reach with every second that passes. None of this is going to change. None of it is a problem to be solved or a condition to be corrected. It is simply the universe being what it is, on its own terms, at its own scale, indifferent to our comfort and our comprehension in equal measure. And yet, within all of that immensity, something extraordinary has happened. Matter has organized itself here on this small rocky world into a form capable of knowing that the universe is immense, capable of measuring the edge of the observable cosmos, capable of sitting in a quiet room on a small planet and feeling genuinely and with full awareness the weight and the beauty and the terror of existing inside something this large. We are the universe noticing itself. I know that phrase has been said before and said beautifully, but I want you to hear it tonight not as a poetic sentiment, but as a literal description of what is happening in this moment. The hydrogen in your brain, forged in the first minutes after the Big Bang, is arranged right now into neural structures capable of representing the Big Bang and the edge of the cosmos and the silence beyond the horizon. The universe has used its own matter to build a device that can model the universe. That is not a small thing. In 13.8 billion years of cosmic history, with 2 trillion galaxies each containing hundreds of billions of stars, we do not know of this having happened anywhere else. It may have happened elsewhere. It may be happening in 1,000 places across the observable universe at this very moment, but we know it is happening here. We know it is happening in you tonight, as your breathing slows and the thoughts loosen their urgency, and the vast dark of the cosmos settles around your awareness, like a blanket made of starlight and ancient time. The edge of the universe will still be there tomorrow. It will be there in 1 billion years, further away, carrying more unreachable galaxies in its wake, the cosmos growing larger and darker and more isolated in its outer reaches. The bubble we inhabit will keep expanding, its walls racing outward at the speed of light through the inflating background we can never observe. The cosmic microwave background will keep redshifting toward wavelengths too long to detect, slowly erasing the record of our cosmic origins from the sky. And the stars will keep burning, for now, filling the observable universe with light that travels for billions of years to reach us. Light that carries in its spectrum the chemical signatures of distant suns, and the confirmation that the laws of physics we know here apply across the full breadth of everything we can see. All of this will continue, patient and enormous and entirely unconcerned with whether any aware mind is present to observe it. But tonight, one is. you are. And that matters, not to the universe, but to the story the universe is telling through you. Before I let you go, I want to say something simple. You spent tonight at the edge of everything. You sat with questions that have no answers and distances that have no analogies and timescales that collapse the ordinary sense of what large means. You did not turn away from any of it. You let it be as strange and as large as it actually is. That is not a small thing to do. It requires a particular kind of courage. The courage to let reality be bigger than your ability to contain it, to find that expansion of scale not diminishing but enlarging, to walk to the edge of the knowable universe and come back feeling, somehow, more rather than less. I hope you feel that tonight. I hope the scale of what we explored together makes the world you return to tomorrow feel not smaller, but richer, not more ordinary, but more remarkable, not less significant, but illuminated by the knowledge of everything it is embedded in. Thank you for joining me tonight. Thank you for staying with me all the way to the edge and back. If this journey meant something to you, if it opened something in you, or settled something, or simply gave you a few hours of quiet contemplation in the company of the cosmos, please take a moment to like this exploration or subscribe so we can make this journey together again. It is a small thing, but it helps these ideas reach other curious minds who might need them. Now let your body be heavy, let your thoughts drift. The next time you look up at the night sky, whether it is tomorrow or next week or on some clear night far from now, remember what you know. Remember that the light reaching your eyes has travelled for millions or billions of years to find you. Remember that the edge of everything visible is out there in every direction, moving away from you at the speed of the light, and that beyond it the universe continues in ways no human mind can fully map. Remember that your atoms are older than the Earth, and that you are, in the most literal physical sense, made of the universe noticing itself. Sleep well tonight. Dream of distant light and ancient edges and the vast, patient, terrifying, beautiful dark that holds everything we will ever know. Keep looking up at the stars. Good night.